Welcome back. We have been talking about forces from external magnetic fields from currents, and now we're going to talk about some of the applications of this technology. Turns out that this is very, very useful. And one of the most useful tools that we use on a daily basis is an electric motor. Most of you may not realize what exactly a motor does, but essentially all it does is it converts electric energy into mechanical energy. And it does that by using electrical energy to pass current through a coil in the presence of an external magnetic field to create a spinning motion. You all heard in our history that fire is one of the big discoveries that allowed our species to get ahead. Wheel was one of the other ones that allowed for a lot of the engineering around the world. Well, what good is it to have a wheel if you can't spin it easily? And rather than people pushing it, if we can have electric energy that causes a wheel to spin, then we can get lots of applications. Just think about things that you use on a daily basis. Every single fan that you use uses an electric motor to make the blade spin. Any car wheel that you see, anything that you see as a regular spinning motion uses the basic concepts of what we're going to discuss in this video. So let's take the example of a magnetic field that's external that's going into the page. This could be caused by a permanent magnet or an electromagnet. We don't care what the source of this is, but there could be a magnetic field going into the page in that region. Now we want to take a current coil and place it here. It could be a circular coil, but just for illustration here, I'm taking a square-shaped coil. And let's say there is a current that goes in this coil in the clockwise direction. So based on what we have done so far, you know that there's going to be a force from this external magnetic field on each of these current segments. Well, let's figure out what the direction of that force will be. So on this top segment, I have the current moving to the right, and I have the external magnetic field going into the page. So I will have to hold my right hand with the thumb pointing in the direction of current, so this way, and then the fingers are all going to be pointing into the page. And in order for your right hand to take that orientation, you will have your palm facing up. So your palm is here, which means the direction of the force on this segment is going to be to the top. Repeat that for the other segments. Just to give you one more illustration, let's take this right segment. Here I have the current going down and the magnetic field is still going into the page, so I will have all my fingers pointing into the screen. And when I hold my hand like this, my palm is over here, so the force will be to the right, and so the force on this segment will be to the right. And when you repeat that, you're going to see that the force on each of these segments is going to be to the outside of the coil, given the orientation of the current we took and given the orientation of the external magnetic field we took. So if this coil is just sitting here, you can see that the net force is going to be zero because there's a force of F pulling up, but there's a force of F pulling down, so those two cancel each other. There's a force of F pulling to the right, but there's a force of F pulling to the left as well. Those two will cancel each other. So you're going to have sum of forces equal to zero. And with the coil standing vertically like this, there is no torque either. So there's going to be no torque. So this guy is just happy staying there and not moving. However, if I take the same situation and let's say I grab this top part of the coil here and pull it out of the screen, rotating it. So when I do that, because of the three-dimensional aspect of this, rather than look like a square when viewed from the front, it's now going to look like a rectangle because it's tilted. So it's going to look something like this. It's still a square, but because I have yanked the top end of this toward me, the bottom end has gone in. So I pulled this out and pushed this in. So it has shrunk in the projection. It has shrunk along the vertical axis. The horizontal axis is still the same. And the forces on this guy are still going to be as we discussed before. None of that changes. The forces are in these directions. But now something interesting has happened. Sum of forces is still 0, but sum of torque is no longer 0. To show you that, let me take a side view of this. So I'm going to take this entire image here and spin it along an axis so that the magnetic field lines that are going into the page are going to go to the left. Okay, so I've taken the entire situation and changed my perspective. So rather than look at it face on like I'm going to look at it from this angle. So this is my viewpoint, which means I've taken this entire thing and spun it. So when I do that, rather than the magnetic fields going into the screen, they're going to be going from right to left. And this coil is now going to look like this. There is a third dimension to it that goes into this page, but all I'm going to see is the top end that was pulled out of the screen, the bottom end that was pushed into the screen, so I see this tilt. So now, on these segments that are shown on the screen, there is going to be a force that's out of the screen on this end and into the screen on the other end. So this force here will now come out of the screen towards my eye. This force here will go into the screen, so those two will cancel each other and not have any effect. But an interesting thing happens with the other two forces. So these forces are acting up and down, and they still cancel each other in terms of total forces. So that is still true. Sum of F will be 0. So this guy is not going to accelerate in one direction or another. But the torque is no longer 0. You see that this force on the top around the center pivot is going to have a torque that makes it want to spin that way. And the force at the bottom is going to make it want to spin that way. So both of those add up to create a torque that's going to make this coil spin in a counterclockwise direction. So it's going to spin in a counterclockwise direction, and then eventually it'll overshoot when it's vertical. There will be no net torque, but inertia will carry this guy, and it'll go overshoot and get tilted the other way. But when it gets tilted the other way, the forces now act still in the same direction. So now the torques are going to be going backwards. So this coil will swing counterclockwise, overshoot the middle point, go to the other side, slow down, stop, and come back and swing this way and go back and forth like a pendulum. That's what will happen by default. And so we have converted electrical energy to a spinning motion, but we haven't caused spin in the same direction. We're going back and forth, which sometimes could be useful, but for the most times it is not very useful. So what do? Well, humans are clever. So what we do is we have created the electric motor where we magically switch the direction of flow of current when it is vertical. And by doing that, we can reverse the direction of the forces on these. So instead of this pulling up, this will, once it goes over, the force is going to pull down because the direction of current is reversed, so the direction of force will be reversed. Oh, by the way, let me just show the direction of current. So this is still on this diagram at the bottom left. The current is going clockwise, which means when I flipped it like I did, the top wire is going to have the current going away from my eye, so into the slide, and the bottom one is going to have the current coming out of the slide, which is what, if you use the second right-hand rule, will give you the directions of the forces as I showed. But once it crosses the vertical, if we are able to reverse the direction of current and make the top one come out of the slide and the bottom one go in, we can reverse the direction of forces using second right-hand rule and make it go this way, which will then cause it to continue spinning in the same direction, which is what a motor does. And I'm going to show you a quick illustration. The tool that's used is called a commutator. So the way we do it is have a north pole here, a south pole here. Some of you are probably having a very uneasy feeling right now. I told you before that there are no magnetic monopoles. So how come it is that I'm showing you a separate north pole and a separate south pole? Well, these don't have to be independent entities. They could actually be connected by a horseshoe kind of magnet where there's a north pole on one end and south pole on the other end. So it's a single magnet, and we're just showing you for the sake of clarity just the ends of it. So the magnetic field of this kind of a permanent magnet is going to be going this way from north to the south. And now if I place a coil here, let me change colors. So let's say I have a commutator, which is essentially a cylinder with a slit at two ends. So it's got a small slit at each of these ends, and it's connected to a battery. So the battery will have a current going in this direction. So the current will go through this wire this way, into the commutator this way, and onto this guy in this direction, and then come back and finish the loop over here. But the interesting thing that happens is because of these gaps, as soon as the coil spins and goes past the gap, when it has inertia, it'll just carry forward. Then the end, this end, which was touching the left end of the commutator, will now be in contact with the right end. And this end, which was in the right end contact, is going to touch the left end. So by doing that, the direction of the current is reversed every time this coil becomes vertical. So then just with this clever invention here, we're able to keep this guy spinning in the same direction for a long time. All right, so we looked at a very important application of a magnetic force on a current loop. We saw how we convert electrical energy into mechanical energy. This causes spinning motions. We use them in fans. We use them on computer hard drives. We use them in cars. You probably use them in your toothbrush if you use one of those mechanical toothbrushes. Everywhere you look around, you see something spinning. And every one of those examples uses this gadget called an electric motor, which in its core has a magnet and has a coil that is passing a current through it. Thank you.